Hello everyone. Today we're gonna look at transistor-transistor logic gates. As you might have known, we've done the diode transistor logic gates previously. Showed you what those look like at the component level. And so now we're gonna show you transistor-transistor logic, and then I think I'll show you guys some CMOS logic. And then we'll move on into you know, other stuff. It's important, I think, to show you guys what this looks like so you can imagine what I'm gonna show you later. As I always allude to, in a way that makes the most sense to you, right? But also so you can see the evolution of the logic families. All right, so here we have the transistor-transistor logic. So if we simulate the circuit, we'll start over here with our NOT gate. We have some resistor values. Typically you might see like 4.7K for your base resistor, but I'm using 10K. It doesn't really matter. You can do your own BJT math to figure out what you want to do. You do have to remember the beta value changes with temperature, it changes with all sorts of different factors. So our NOT gate here, well, if we jiggle on the input here, you see all it does is invert. And you might have noticed it looks very. I showed this in DTL video, I think, but you can see that kind of much like the DTL, we have a voltage traveling through this base resistor into this transistor and out the emitter. So when you actually, send a signal through the emitter, well, the signal still can flow through the emitter into the, through the collector and leak through into the base, but the majority of the current is flowing from the 5-volt line. Unlike the diode, which completely blocks the flow of current, some current can still leak through. That's pretty cool, I think, but not much different than the diode transistor logic. We've just, have made it so that we're using transistors instead of diodes. Now for our NAND gate, well, it's, much like our NOT gate. All we did was, in the same fashion as our diode transistor, we just threw another input here, another transistor, as opposed to another diode, if you relate it back to the diode transistor logic. So, we can send current this way, but now the current, so it can't travel through this emitter and into ground. So instead it'll travel through this transistor down here. And so if we were to send a signal through this transistor as well as this transistor at the same time, well, then you have your low output. And then obviously, our AND gate is just inverting the NAND gate's output, so both of these have to be high in order for you to get a high output. So you can see that takes 5 transistors, and then only 4 resistors. I don't know if you can reduce it any further. And if we come over here, we can take a look at the NOR gate. So the NOR gate, much like our DTL gate, we have 2 transistors in parallel that feed into the same output here. And so, one or the other, and that's our NOR gate. Basically just an inverter again, since it's just 2 of these gates in parallel. And then of course you invert the output, and then you have your OR gate. Very simple. You can see the way the current flows in here. Pretty cool stuff. And then of course we have our exclusive OR gate. So anyway, I think I just accidentally changed the value of that. So moving on from our other gates, we have our exclusive OR gate. And this one's made with 4 NAND gates. It might not be very clear with these examples. I've tried to compact them all as close as I possibly can to, not take up as much space. I realize that might have been a nightmare for showing, or showing it to other people. But if you know the diode transistor logic, it's almost identical. We just changed our diodes out for transistors. That's really what you can think of it as. So for our exclusive OR gate here, we have one or the other, but never both. And obviously, if I wanted to make this an exclusive NOR gate, we could just throw a inverter on the end. I don't think anybody uses exclusive NOR gates. They have a use, I think. I might have mentioned it once upon a time. But yeah, that's basically your transistor logic. You can really see how the evolution from diode transistor logic to transistor logic happened. A lot of the same principles are applied A lot of the typical same values are used as well. And yeah, I mean that's really it. I mean there's not much else I can really say. I mean next we're gonna see what CMOS looks like, so stay tuned for that.